In this segment, we'll look at how to deal with the recurrence relation for Mergesort. So first, let's look at what we have for Mergesort. So there's a few things going on. So we want an expression of t of n, the runtime for Mergesort, in terms of the recursive calls. And the recursive calls are going to be the runtime function on smaller input sizes. And there's a couple things that we want to point out. So we're assuming that for the base case, so if we just have a list of size 1, or size 0, we can return in constant time. Now, we want to be able to express the runtime of Mergesort in terms of itself, so smaller sizes. So one thing that we want to note is that merge, as we saw before, takes linear time. So this step inside Mergesort is going to take C times, I'll just call this C2, times some, that's just some constant times n, so linear time. And now we know that just updating the midpoint is constant time, but now we're worried about these recursive calls, and we know in the recursive calls we have to divide the list in half. So that's we're going to make a call for a list of size n over 2, where n is the size, my list size. And we'll make another call for n over 2 to do the second recursion, divide and the second recursion. So from this, what we can see is that the recurrence relation for Mergesort is going to be t of n. We have the constant, which I'm just going to ignore to get the midpoint. And then I'm going to make 2 calls of size n over 2. So that's my t of n over 2, plus the work for Mergesort, which is going to be linear time. So that is my recurrence relation for Mergesort. So now we want to think about how can we actually solve what this is going to be. And there's a few techniques that we can use for this, and I just want to show you some of the more intuitive ones now. So one technique is a recursion tree. So for the recursion tree, we want to think about the input sizes in each of the calls, and then we want to figure out the amount of work that needs to be done. So when I'm drawing a recursion tree, I like to just draw it in terms of the runtime. So here, at my root is going to be my call of size t of n. And once I have my call of t of n, as we saw, I'm going to make 2 recursive calls. And I'm going to make a recursive call on size t of n over 2, and another recursive call on size t of n over 2. Those are my next nodes. And then you'll notice that each of these would have to make a call on n over 4. And so forth. And we're going to keep on, and I'm not going to obviously draw the whole tree, but you can see that we have a pattern going on. So then I'm going to put some ellipses that we are going to keep on until we get to the layer where we're just making the calls on T1, which is the base case. And there's going to be n of these nodes at the bottom. I think I'll draw that a little bit more neatly, but you'll see that we're just doing n of these now. That's hitting the base case. Okay, so once we have our tree, and we should have n of those, we want to add up the work that is done on each level of the tree. And I'm going to change to green for this. So on this level, we're doing a constant amount of work, but there will be n nodes. So we're going to have some constant amount of work times n, 1 for each of those. So we're going to get our NC term here. Now, you'll notice that if we look at the tree a little bit higher, you'll notice that for the top recursive call, we have to do linear amount of work. So I'm just going to call this some constant. Also, we're not being so careful about the constants, but we can use different, the same, doesn't really matter. And here we're going to make 2 calls that are going to be doing n over 2 work, sometimes some constant. So here we're going to have C2 times n again. And here we're going to have 4 calls doing n times 4 times some constant amount of work. Is you'll notice then we have see it again. And here, this ellipsis, what we're going to do is that you'll notice that for the layers, for each of the layers, so at the very top level, I have just n divided by 2 to the 0. On the next level, I have n divided by 2 to the 1, then n divided by 2 to the 2. So then in the middle here, we are going to have 2 to the k recursive calls, all doing n divided by 2 to the k amount of work, which gives us just c of n. So now we see how much work is being done on each level of the tree, and then we have to worry about how many levels. How many levels can we have on this tree is the number of levels is going to be log base 2 of n. And we've already discussed that, because here we are observing that 2 to the log base 2 of n is just equal to n. So this is the number of times that we can keep on dividing our list in half until we hit a base case. So what do we have to do? We notice that each of the levels takes nc work, and there are log levels. So the total is going to be c times n times log 2 of n. Now, we were a little bit casual in this, right? Because we're just approximating the work done on each level, but it's a pretty good claim. But we have to be a little bit more precise, because when we hit the base case, for example, the log of 1 will just be 0, and we're not doing 0 work for that. So now we can write our recurrence relation in a closed form, and here we just have to take into account that for the base case. So here we can say we're doing some constant times n amount of work, 1 for the base case, plus the log 2 of n. And we don't have to necessarily worry about the constant so much, because this will give us the asymptotic bound that we need, which is just n log n. And you may be wondering, okay, well, what would I do once I have this closed form here? What can I do with it? Well, the way that you can actually solve this, the way to actually handle this, is through a proof by induction. In the proof by induction, so we would prove the claim that the runtime is equal to n times 1 plus the log 2 of n by induction. And this you can do as